Hello, everyone. Today we continue with solving a few problems from your homework, the homework you handed in, and also probably we would practice a little bit more for the homework you're supposed to do. Um, Also, I want to kind of, if I can, I'm not sure if I can. I want to share some of the homeworks that I'm grading, well, without showing your name, to tell you some of the common mistakes you make while solving a problem. That might be useful um, in order to learn how to solve problems without those mistakes. Okay. First, before I start, is there any question? Okay, if not, let's start. Okay, let's start with a quick review of your homework. So the first problem was this one. So problem number 1. We had a linear map. Suppose T is a linear map from C3 to C3, such that T of 1, I, and 0 is equal to -1, 2, 3, and T of 0, 1, 1 is equal to 4, 5, 6. And then the first part of the question was this. Explain why a map T satisfying these conditions exist. Why a map T satisfying these conditions, the conditions above exists. Okay, so the answer to this question is pretty simple. The reason I want to write the answer carefully here is that although the answer is simple, but while I was going through your answers, I guess some of you still know what is the answer, but you are not quite sure how to write that. And that's important. Knowing how to write a mathematical argument is an important part, even if you know the argument, okay? Okay, so let's look at this problem. We have two vectors, and this map is defined, the value of this map is defined for those two vectors. So C3 is a three-dimensional complex space, right? It does not look like this. It's what I drew here is R3, C3. The real dimension really is 6. The complex dimension is 3. But let's just, for having visual, let's consider that. So we have a map from C3 to C3. And we know the value of C on 2 points, 2 vectors, these two. And now I want to say why such a map T really exists. So remember, we can define linear maps by only defining their values on basis, right? Or on linearly independent vectors, which they generate all the space. So there are two possibilities. So whenever we have, more generally, whenever we have a linear map between two spaces, two vector spaces, V and W, we only need to define the value of T on a basis, the elements in the basis. If we know that, then if we know the value of the linear map on the basis, then we know the value of T everywhere, okay? Now, if we know the value of T on some linearly independent vectors, we can always, that's a theorem, we can always extend, if we have a few vectors which they are linearly independent, we can always extend those vectors to a basis. So whenever you have a few vectors, so V1 up to Vk, which they are linearly independent. linearly independent. It's always possible to extend them to a basis for your vector space up to vk, and then vk plus 1 up to some vn, where this new thing is a basis. Okay. Now, if we have the value of t, for example, if t is defined here, if t is defined for v1 up to vk, there's a way to extend the value of t to v1 up to vk, vk plus 1 up to vn. Well, t is defined here, and here you can define it any way you want, arbitrary. Okay. So the only time that these things, which I said, these things don't work, is when we have a few vectors v1 up to vk, which they are not linearly independent. There is a linear combination between them. So suppose these vectors are not linearly independent. When they are not linearly independent, it means there is a linear relation between them. Okay, it means there are elements in the field, whatever the field is. I show the field here with F. The field might be R, might be C, it might be other fields. It means there are elements in the field A1 up to AK, which it's not true that all of them are 0. So some of them are non-zero, or at least one of them is non-zero. So there are elements in the field where at least one of them is non-zero. And the linear combination A1 times the vector V1 up to AK times the vector VK is equal to 0. In that case, if the value of t is defined on these vectors, the value of the t on these vectors should satisfy exactly the same relation. What do I mean by that? So here we have vectors v1 up to vk in the domain. In the codomain, we have t of v1 up to t of vk. Now, for v1 up to vk, we have this linear relation. We should have the same linear relation for t of v1 up to t of vk. Why is that true? So look at this relation here we have. Let's apply t to both sides of this equation. So we would get t of a1 v1 plus up to ak vk is equal to t of 0. But we know for any linear map, t of 0 is equal to 0. So the right-hand side is equal to 0, right? On the other hand, t is linear, and linear maps respect or preserve the addition structure. That means t of a1 v1 up to plus up to ak vk is equal to t of a1 v1 plus t of ak vk. That's part of the definition of a linear map being a map being linear. The second property of linear map is that it respects the scalar property, right? So t of a1 v1 is a1 t of v1 plus up to ak t of vk. Remember, on the other hand, it is supposed to be 0. So if you look at this relation, you would see we want t of v1 up to t of vk. They satisfy this linear relation. So the image of these vectors in the codomain, they satisfy exactly the same relation as the vectors themselves. So for example, if I have 3 vectors v1, v2, v3, for example, over say in a vector space over real numbers. For example, if I know, say, if I know 2 times v1 plus 3 times v2 plus 4 times v3 is equal to 0, for any linear map, I can look at T of v1, I can look at T of v2, I can look at T of v3. They should satisfy the same relationship. We should have 2 times T of v1 plus 3 times T of v2 plus 4 times T of v3 equals 0. So if they give me a map, T, which does not satisfy this equation, then that map can't be linear, okay? So very simple example. Suppose I have R3, which is easier to think about, easier than T3. And suppose I have a linear map from R3 to R3. Suppose a map T is given by this definition, not completely, we only know about map T with this thing, that T of 1, 1, 1 is equal to, say, 1, 2, 0. And also T of 2, 2, 2 is equal to 3 minus 2, 1. And then they would ask us, is there a linear map T satisfying these properties? The answer is no. So is there a map T? Is there a map T satisfying these properties? And the answer is no. Why? Because if I take v1 to be this vector 1, 1, 1, and if I take v2 to be this vector 2, 2, 2, there is a relation between them. 1 times v1, 2 times v1 plus minus 1 times v2 is 0. We can see that 2 times v1 plus minus 1 times v2 is 0. So the image of these two maps should satisfy if T is supposed to be linear, assuming T is linear, there is a linear map with this property, then we should have 2 times T of v1 plus minus 1 times T of v2 equals 0. But is that correct? 2 times T of v1, 1, 2, 0, plus minus 1 times T of v2, 3 minus 2, 1. What is that? Well, that's 2 minus 3, that's minus 1, 4 plus 2 is 6, and then minus 1. This is obviously not the vector 0. Okay, so the answer is no. Now, going back to your homework, we have 2 vectors. V1 here, so the vector space itself is C3 over the field of complex numbers, not real numbers. That is important. And the vector v1 here is 1, I, and 0. And the vector v2 here is 0, 1, 1. So is there any relation between these 2 vectors? Is there any linear relation between these 2 vectors? So what do I mean by that? Can we find, so that's the question, can we find 2 elements A1 and A2 in the field, which here is the complex numbers, such that A1 V1 plus A2 V2 is equal to 0? Do we have such a thing or not? Okay, let's try to first understand and address that question. So A1 V1 would be equal to A1 times 1, A1 times I, and A1 times 0, which is 0, plus A2 times V2, A2 times 0, A2 times 1, A2 times 1. That would be A2 times V2. What is their sum? Their sum is A1 plus 0, I A1 plus A2, and 0 plus A2. This should be 0. That implies A1 is 0, I A1 plus A2 is 0, and A2 is 0. So look at these 2 relations. A1 is 0 and A2 is 0. So for any 2 such A1 and A2 satisfying this property, both A1 and A2 are 0. So there are no pair of complex numbers which both of, well, at least one of them is non-zero, and they satisfy this equation. That means, so this is the first part of, so when I want to answer this question, the first thing is I should understand if these two vectors are linearly independent or not. This part tells me v1 and v2 are linearly independent. So that's the first thing I should write. v1 and v2 are linearly independent. So some of you in your solution, you've written they are obviously linearly independent. Yeah, that is obvious, but this is the course to prove that, right? This is linear algebra. Here, for us, it's not still obvious. We need to prove that. Okay. So now that they are linearly independent, it means there is no linear relation between them, and therefore there is no linear relation which there should be between the image of these two things. So there is nothing left to check. When they are linearly independent, T of V1 and T of V2 can be anything. It's arbitrary, right? So when they are linearly independent, when V1 and V2 are linearly independent, T of V1 and T of V2, when we want to define a linear map, these things can be anything. They can be anything. And we can always extend that to a linear map. V1 and V2 are two vectors in a three-dimensional space. C3 is a three-dimensional. We can always find V3. We can define T of V3 anything we want. When they form a basis, we can define T of V3 anything. For example, say I would take it to be 0, the 0 vector. And then I have a linear map because it's defined on the basis, and I can extend it linearly to the whole C3. Okay, that's the answer of the first part. So I should say one of the common mistakes I saw in the solutions was this. So a lot of people have mentioned these two vectors are linearly independent, and therefore their images have to be linearly independent. And then if you look at the question, it says the image of the first one is this, and the image of the second one is this. And some of you prove these two vectors are linearly independent. Here, that's not true. We don't care about that. That doesn't have anything to do with the proof. We should look at the relations in the basis, in the domain, and then the same relation should hold for their images. But here there is no relations for these vectors in the domain, so there is no relation that must hold for their image. Okay. And then the second part, so the first part of this question, you should first say T, there is such T because V1 and V2 are linearly independent. And then you should also prove that, and you should prove it. That would be the solution for the first part. For this, the second part says why these conditions, why the map T satisfying these conditions is not unique, why there are different maps T satisfying these conditions. So I kind of answered that question. Here we have two vectors, but they are linearly independent, but these two vectors, they do not generate the whole C3. Their span, the span of these two vectors is not the whole C3. We still need a third vector to generate all C3. So I can take that vector. Well, there are a lot of different choices. That doesn't matter. So we have this vector, we have this vector, and then we can choose a third vector, V3, such that their span is the whole C3. We know that as a theorem, any set of linearly independent vectors can be extended to a basis. Now, the part that gives us the non-uniqueness property is this part. I can define T of V3 anything I want. I can define T of V3 anything I want. This is arbitrary. The value of T of V3 is arbitrary. So the non-uniqueness, it does not come from the choice of V3. I mean, it comes from the fact that any V3 I choose, the value of the map on that vector can be anything, okay? And then I can extend it linearly to all C3. And because it can be arbitrary, it can be anything inside C3, it gives me the non-uniqueness. So if I want to write down the answer, I would say because V1 and V2 do not span the whole C3, there is a third vector, which together they can generate all C3, and the value of the map is not defined on that vector. That can be anything, and that gives me the non-uniqueness property. Okay. Any question from any problem with this one? Is it clear? Okay. So let's take a look at the question number 2. We have a set of points, x equal to P1 up to Pk inside C to the n. It's a finite set, k elements. And then we say a map T from Cn to Cm extends a map. So a map T from Cn to Cm extends a map F from X to Cm if well, X is a subset of Cn, so T is also defined on X. So if I restrict T to X, if I look at the value of T on the elements inside X, which there are P1 up to Pk, it is equal to F. In other words, if T of P1 up to Pk is equal to F of Pi up to Pk. Okay, that's the definition of an extension of a map. Now, the question is that we have, what is the condition? So what is the necessary and sufficient condition? So what is the necessary and sufficient condition for existence of such map? What is the necessary and sufficient condition on X? Maybe it's better to say it on X for existence of a linear extension.
I guess that's all vectors in X are linearly independent.
That is correct. So yeah, thank you. So first, I should mention one thing. There was a lot of misunderstanding in the solutions, and I can understand that why. So some of you have thought that the question is asking what is the necessary condition? So you had one answer for that part, and what is the sufficient condition? And you had an answer for that part. But actually it is asking for a necessary and sufficient condition together. It's not asking for a necessary condition for existence and for sufficient condition separately. It's asking for a condition which is both necessary and sufficient. These things are, so we are looking for one answer, first of all, and that's one thing. So let's now look at that. It's very similar to the previous question. There I mentioned if the vectors, if you have some vectors and there is no relation between them, I can define a map on these vectors arbitrarily with any values I want, and I can always extend it linearly to the whole space, okay? So if so, so the answer is the elements in X, P1 up to Pk, they should be linearly independent. So that's the answer. Why? Now I should prove that. So there are two parts. When I say necessary and sufficient, it means there are two parts. First, I should show if X satisfies this property, if these vectors are linearly independent, then there always exists a linear extension. And conversely, the other direction, if I can always find a linear extension, if linear extension exists, if linear extension exists for every f defined on X to Cm, then I should show these vectors are linearly independent. So there are two things which I should prove. Let's look at the first part. Let's first assume the elements in X are linearly independent. Why can I always extend a map F to a linear map? Well, P1 up to Pk are linearly independent. We know that any set of linearly independent vectors, we can always extend them to a basis of all the space. So we can extend them. It's possible to extend them to a basis. Now, for any f, I know what is f of P1 up to f of Pk. I can extend this map by defining it anything I want on the other vectors. So define f or t by any value you want on the other things. So so P1 up to Pk, they are already defined. It goes to f of P1 up to f of Pk. And then for Pk plus 1 up to Pn, I can define it anything I want. I would choose the simplest one. I can say, let's send all of them to 0, right? Just one simple choice. And then I have a map defined on a basis, And whenever you have a map defined on a basis, you can linearly extend it to all the space, to here Cn. Okay, we know that whenever we have a map defined on the basis, we can define it for every element there. Now, conversely, I want to show if any map F from X to Cm can be extended to a linear map T from Cn to Cm, then the elements in X, which means P1 up to Pk, they have to be linearly independent. They are linearly independent. So it's the other direction. So the way I prove that is like this. So sometimes rather than doing the direct proof, we can use a little trick. I want to say they have to be linearly independent. So I would say, what would happen if they are not linearly independent? Okay, it's kind of like proof by contradiction. So suppose they are not linearly independent. What does that mean? It means there are elements in the field, which here they are in C, which at least one of them is non-zero. So at least one of them is non-zero. So Here, I can assume, for example, A1 is non-zero. Why? Because one of them is non-zero, I can just call that thing A1. Even if it's A2 or A3, you know, this is just a notation. I can choose the letter A1 for that non-zero element. So without loss of generality, I can assume this is A1 that is non-zero. Okay? So there are A1 up to AK, where A1, P1 plus up to AK, PK is equal to 0. So we have a linear relation between these. Okay. So it means A1, P1 is equal to minus A2, P2, minus A3, P3, up to minus AK, PK. Because A1 is non-zero, I can divide everything by A1, right? So if I divide both sides by A1, on the right-hand side, I would get minus A2, P2 over A1, etc. Now, what was the assumption? The assumption was any map F defined on P1 to PK can be extended to a linear map. Now I'm going to construct a map F defined on P1 to PK, which can't be extended. And that would be a contradiction. And that would complete the proof because we're doing proof by contradiction, right? So define the map F where F of P2 is 0, F of P3 is 0, up to F of PK is 0. But I would define F of P1 something non-zero. Say I would define it to be 1, 0, 0. They are all 0. They are zeros in CM. Remember, F is a map from Cn to Cm. So we can think about them as 0 vectors. Okay, so F of P2 up to PK are 0, but F of P1 is not 0. And that's a contradiction, right? Because if I apply F here, on the left-hand side, I have F of P1. On the right-hand side, because we want it to be linear, it would be equal to minus A2 F of P2 over P1 A1 minus up to, okay, I continue here, AK F of PK over A1. Now, F of P2 is 0, F of PK is the vector 0. Everything on the right-hand side is 0. So the right-hand side is equal to the vector 0. But the left-hand side, I defined F to be 1, 0, 0, 0. So the left-hand side is non-zero, whereas the right-hand side is 0. And they can't be equal. Here we have equality between something which is 0 and something which is non-zero. That's a contradiction. So that's a contradiction. What was the assumption which got us to this contradiction? The assumption was that the elements in X, they don't have to be linearly independent. We assume there is a linear relation between them. And that got us to this contradiction. So they have to be linearly independent. That completes the proof. Okay. Any question here? Okay. Okay, so the second part of the question says, formulate conditions on a map F from X to Cm. Form conditions, so conditions on F as a map, which is necessary and sufficient for existence of a linear extension. T from Cn to Cn. What is the answer here? What is the necessary and sufficient condition on F, the linear map, so we can extend it to a linear map? Now here we don't know if the elements in X are necessarily linearly independent anymore. So suppose there might be some relations between the elements in X. So what would be the condition on F to do that?
Have F be linear?
Well, F is not, well, you're kind of right, but remember, linear, a map is, when can we say a map is linear? At least it should be defined between vector spaces. The domain of F is not even a vector space. It's just a set of some vectors.
I mean, like, F is linear in its arguments. Like, you can treat them a linear map.
Yeah, it's fine. Yeah, yeah, you're right. So the correct way to say it, because we still can't say it's linear in its arguments, because again, it's not defined on a linear space. So, but I understand what you're saying. What you want to say is that if X is any set of points, if we can find elements in X having some linear relation, for example, if there are, suppose there exist elements v1 up to vk in X, which they have some linear relation, then the property for F is this: the value of F on v1 up to vk should still satisfy the same thing. So we kind of talked about the proof of this one too. I'm not going to write this one more in detail, but so yeah, if it does satisfy that, then we can extend it to a linear map. And well, it's necessary and sufficient condition. And then the last part of the question, formulate a sufficient condition on X under which any two linear extensions of the same map coincide. So let's just look at the last part too. So what is the sufficient condition on X such that any two linear extensions, T1 and T2, are equal? What is the answer to that part? Does anyone know?
X should span the entire input space.
That is correct, yeah. So X should span, the span of X should be all space Cn. Because if it does not span all the space, there is a vector outside of the span of this thing. So if not, there would be a vector v in Cn minus a span of X. And then I can define the value of this extension on V anything I want. Therefore, it's not unique anymore, right? So then T of V would be arbitrary. And then it means it is not unique anymore. Yeah, that is correct. So that's kind of a review of the homework we had this week. Let's take a look at some other questions. Is there any question here? I think I would finish grading it today, and then you can take a look. And if you have any question, or if you think I made a mistake in grading, like, make sure to let me know. Okay. Let's solve some other problems. Okay, let's do a little bit computational problems. I think you probably are good with computational problems, but it's good to practice. So let's start with this. Suppose we have a map T from R3 to R3 defined by this property, defined like this. T of x, y, z for any vector x, y, z in R3 is equal to 2x plus y plus 6z and 5x plus y and 7x plus y minus 4z. Okay. So first, find the kernel of T. What is the kernel of T? Okay, you can think about it just maybe for a minute because we don't have much time, and then I would start writing it. It's a good practice. Okay, let's do it. So we want to find the kernel of T. So we are looking for the vectors x, y, z such that T of x, y, z is equal to 0. So it means the first component should be 0. The second component should be 0. And the third component should be 0. Well, in some sense, this is an answer, but we want to kind of characterize the elements in this space. Let's see what I mean by that. So we want to have these three equations. We want it to hold for x, y, and z. So let's say I multiply the second and third vector by 2. I would get 10x plus 2y is equal to 0. And 14x plus 2y minus 8z is equal to 0. Okay, we have an answer. I think the answer is correct, yeah. So, and then let's just write down the first one. Okay. Now I can kind of combine these equations, right, to get some easier problems. Can anyone tell me how I can combine these things to kind of get rid of, for example, let's say we have x in all of the equations. Can I, for example, get rid of the variable x in the second and third equations? Is that possible?
Yeah, don't you just subtract the first equation from them, but then multiply by like 5 and 7, depending on
So
which
yeah,
one
that is correct. So if I multiply the first equation by 5, so equation number 1, 2, 3. If I multiply the first equation by 5 and subtract it from the second equation, what would I get? So I have the first equation, I would keep that. I multiplied by 5, I would get 10x plus 5y plus 30z. And then I subtract it from the second equation. The result would be 0x minus 3y minus 30z equal to 0. I want to do the same thing for the third equation. I would multiply that by 7 and I would subtract it from the third equation. I would get minus 5y plus minus 50z equals 0. And then I can simplify it a little bit more. I can divide the second equation by minus 3. I would get y plus 10z equal to 0. And I can divide the third equation by minus 5. I would get y plus 10z equals 0. And then I have the first equation. Now, the good thing is that I can see the second and the third equations are the same. So one of them is enough. I can get rid of the third equation. So there was really two equations, two linear equations, right? The third one is not really necessary. So I have this system. 2x plus y plus 6z is equal to 0 and y is equal to minus 10z if I take minus 10z to the other side. So I can fix some variable here. Let's say I take z to be the variable. I would call that t. T can be any real number. So I would allow z to be anything it wants. It can change. And then y is minus 10z. So it would be minus 10 times t. Now let's substitute them inside the first equation. Okay, so the first equation is 2x plus y plus 6z equal to 0. So, well, z is t, just a variable parameter t, which can change. Y is minus 10t, and I'm looking for x. So 2x is equal to 4t, and therefore x is equal to 2t. Therefore, the points of the form x, y, z are equal to 2t minus 10t and then t, which is equal to the vector 2 minus 10 and 1 times the variable t. So actually the kernel of our map is, well, I can say the kernel of our map is the span of this vector, because the span of this vector means multiply this vector by any real number you want. And that would be the kernel. Okay, any question here? So this notation usually means a span. I wouldn't write span anymore. When I add this thing, that means the span of the vectors inside that. Okay, if there is any question, we can. Oh, we still have time, right? Every time I'm a little confused about time. Let's see. I think we still have a few more minutes. Yeah, it's true. We have 6 more minutes. Okay, we can continue a little bit more. Okay, let's see. Okay, let's do a little bit more computations. So we talked about kernel. The other important property of a linear map is about its image, right? A linear map, we think about its kernel and its image. These two things are quite important. So suppose I have a linear map T, say from R2 to say R4. And suppose this linear map is defined for any x by multiplication by a given matrix, okay? Where this matrix in a fixed basis of R2 and R4, in the standard basis, this matrix is equal to 2, 4, 0, 2, 1, 0, 1, 2. Now the question is kind of understanding the image of this map. So for example, is the vector v equal to 8, 3, 1, 4, is this vector in the image of T or not? Okay, let's think about this one for a few minutes. Okay, let me write down the answer. So we are looking for a vector like x and y in R2 such that a times x and y is equal to this vector 8, 3, 1, 4, right? But what is a times x and y? A itself is equal to 2, 4, 0, 2, 1, 0, 1, 2. If you multiply that by, well, I think it's better to, well, it's okay. What is the result of this multiplication? It's 2x plus 4y, 0x plus 2y, 1x plus 0y, and 1x plus 2y, right? And we want this thing to be equal to this given vector v, 8, 3, 1, 4. Now we should set them equal. If we do that, we get some equations. We get 2x plus 4y should be equal to 8. So the first element of each vector should be equal to the first element of the other vector, and etc. 2y should be equal to 3, x should be equal to 1, x plus 2y should be equal to 4. Now, there are two equations here which they are better to work with. And there are these two, because they explicitly tell us what are the values of x and y. So one of them says x is equal to 1, and the other one says y is equal to 3/2. Now it only remains to see if these solutions, they satisfy the other two equations. If that's true, then this is the answer to this set of equations, right? So let's say 2 times 1 plus 4 times y, 3/2, is equal to 2 plus 6, which is equal to 8. Yes, the first equation holds. X plus 2y equals 4. X is 1 plus 2 times y, 3/2, is equal to 1 plus 3. It's equal to 4. Yeah, the last equation also holds. So x equals to 1 and y equals to 3/2. That's a point which t of that is equal to that given vector v. So the answer is yes. Okay, now the time is really up. So is there any question?
Could I ask a brief question about homework 2?
Yeah, sure.
So, particularly for the second problem, it asks about whether or not linear maps can be expressed as compositions. And it says like let U, V, and W be finite dimensional vector spaces. And so my question was, are those spaces sort of assumed to be given to us at the start of the problem? So we have to figure out what maps can be represented as compositions through these given spaces, or can we sort of choose the spaces we need to create a composition?
So yeah, so the question says let U, V, and W be finite dimensional vector spaces. And then it asks you about the maps between them. So when it starts with that sentence, let U, V, and W be something, it means they are fixed, they are given. You know, we can't change them.
Okay.
Does that make sense?
Yeah, so
Yeah.
we have to sort of figure out, given these vector spaces, how could we create a composition in between
Yes,
the
yes,
three of them?
exactly.
That makes it harder.
Okay, so that's great. That's enough for today. You can also attend my MLC and office hours if you have any more questions. Goodbye, guys.